I should preface my introduction by saying that actually this is also, besides being a keynote speech, a co-host plenary speech, because Dr. Klir's Center for Intelligent Systems is one of the co-host organizations for this conference, and we're very grateful for his support. Professor Klir is well known to many members of this organization. He's a longtime member of ISSS and a former president of the ISSS, and he is, in addition, the director of the Center for Intelligent Systems in the Department of System Science and Industrial Engineering at the State University of New York in Binghamton. We've had, in fact, a number of people here from Binghamton this week. Among other things, he was the founder and a past president of the International Federation of Systems Research, and he is the author of a total of 16 books and edited works, as well as, of course, many published papers, and currently edits the International Journal of General Systems. His research work and writing is currently in the area of uncertainty in fuzzy systems, and also the other topic he will be talking about today, intelligent systems. And let's hope at the end of this week that this is an appropriate topic for us to be discussing here this morning. It's with great pleasure that I welcome Professor Klir.
Thank you very much, Peter. I will be talking today about intelligent systems, and I would like to answer the three questions which I believe you have had a chance to read already. Now, because of the very tight schedule, we have only 30 minutes, less than 30 minutes. I think the answers to these questions will be rather quick, because I would need at least half an hour to answer properly each of them, and I have only less than 10 minutes for each of them. So let me first start with defining what I mean, or what we mean by intelligent systems. Here is the definition. So by intelligent systems, we consider human-made systems. So we are talking about human-made systems, that's important, that are capable of achieving highly complex tasks in a human-like, intelligent way. Now this qualifier, human-like, in the area of intelligent systems is taken seriously. And that is where the new area, relatively new area of intelligent systems somewhat deviates from the current mainstream in the area of artificial intelligence. In artificial intelligence, the focus is not necessarily on the human-like, but in intelligent systems it is taken seriously. And because it is taken seriously, it raises certain questions. The questions are why human beings can perform certain tasks which are taken for granted and considered not tremendously difficult, and yet those tasks current machines cannot do, or it is difficult for them to do. Now, typical example or canonical example is we can drive cars in cities, in a heavy traffic. Like yesterday when I was driving in Toronto, I was thinking about that, how I can be replaced here by a machine who would drive and by instructions, you know, we want to go somewhere. We can park, we can drive in the city, we are able to find a place for parking, and we park the car on the street. We can do that. Now, how a machine would do that? Almost impossible at this time. So what we need is we need to look at how we are doing that and see, you know, why the current machines cannot do that. And if we look at that very carefully, we can see that when we perform these tasks, then we do not do a lot of measurements and collect numbers and then manipulate those numbers and so forth. We do not do that. We basically use perceptions. We perceive the overall situation and then somehow, you know, process these perceptions and act upon that. So we do not deal with numbers here, but we deal with perceptions. Now, perceptions involve a lot of uncertainties. That's the point. We are not concerned whether we are 0.7 millimeters from the, from some place, but we just approximate. We just approximately look at the distances and so forth. And so we do not, the traditional, let's say, mathematical analysis and the traditional logic, which is based on hard boundary, something is true or false, is not really applicable because there is a lot of flexibility, a lot of uncertainty involved in these perceptions. Now, I have an interesting quote here from a book by Edward Bono, which is called, the book is called I Am Right, You Are Wrong. And in that book, he introduces something, what he calls a water logic, and he compares it with rock logic, classical two-valued logic. And he says, for 24 centuries, we have put all our intellectual effort into the logic of reason, the classical two-valued logic, rather than logic of perception. Yet in the conduct of human affairs, perception is far more important. Why have we made this mistake? And then he talks about the principle of contradiction, which can really apply only if the two proposed categories are truly mutually exclusive. In practice, this is very difficult to find, so we deliberately set up such mutually exclusive categories, and these are our treasured dichotomies. Without them, the principle of contradiction and certainty of our logic are greatly weakened. And then he elaborates on that and so forth. Now, this is one of the problems that if we are committed to the classical logic and to the classical analysis and so forth, working with numbers, then we have difficulties in designing these machines. So we have to go beyond that and try to develop something like a logic of perception or whatever he talks about. Now this, of course, involves the issue of uncertainty. Perceptions involve a lot of uncertainty. Now, how can we deal with uncertainty? Well, traditionally, we dealt with uncertainty purely in terms of probability theory. Probability theory was kind of the classical way of dealing with uncertainty. But, again, looking at this parking of the car and so forth, probability theory would not help us, So we need to look at uncertainty from a much, much broader point of view. And unfortunately, it hasn't been appropriately developed. And uncertainty as a concept hasn't been systematically studied in science. It was always kind of considered as something which we try to avoid in science. We must live with that to some degree, but we do not like it. We try to avoid it and so forth. Now, what we are saying now is that human beings utilize the uncertainty in some way. It has a great utility. So if we recognize that need, then certainly the next step is to study uncertainty in a very comprehensive way. Now, and go beyond the classical notion of probabilistic uncertainty. Now, how to do that? Well, I have this two-dimensional kind of matrix which shows that there are two dimensions in which we can extend our view of uncertainty. One dimension is that we have here formalized languages, and of course the classical formalized language is classical set theory and the associated classical two-valued logic. And now, recently, we developed some other more general formalized languages, such as theory based on fuzzy sets, on rough sets, or various combinations of these. Fuzzy rough sets, rough fuzzy sets, etc. Now, these are formalized languages which help us, which are instrumental in representing statements in natural language. In natural language, with all its vagueness and so forth, this classical formalized language of set theory and classical logic is not just sufficient. Because in natural language, we have a lot of vague terms, a lot of vague concepts which just do not, which cannot be properly described by using sets which have sharp boundaries and propositions which are either true or false, strictly speaking. We need the gradual transition from the truth to the falsity, from the membership to non-membership. So clearly, fuzzy set theory as a formalized language is much more capable of describing propositions in natural language. And natural language is a good tool by which we can at least approximate the perceptions. In fact, when we learn the parking, or when someone learns to ride a helicopter or something, the initial way of describing what to do is described in natural language. And then comes the training process. So it's a first instruction natural language, and then the training, following the instructions in natural language, and then the tuning sort of via, the actual experience, trying to do that and so forth. So natural language is a kind of connection from perceptions to the action. It's a good approximator of the perceptions. So that's what's going on here. Now, when we talk about fuzzy sets, of course, there are not only one type of fuzzy sets. In fact, I identified 8 different types of fuzzy sets. I have no time to go into details. I have transparencies, but no time. So there are different types. For example, the basic fuzzy set would be a set where the membership of objects in the set is characterized by a simple membership function, and the degree of membership is described by a value in the unit interval between 0 and 1. The larger the value, the more the object belongs to that set. So that's a very basic standard fuzzy set. But then you have other types of fuzzy sets. For example, fuzzy sets in which the membership degree is not described by a single real number, but is described by an interval of real numbers. Or you can have a fuzzy set where the membership degree is described by a fuzzy number, which is a fuzzy interval. And this would be called fuzzy set of type 2. Then you can go to fuzzy set of type 3 and so forth. So, and there are other types. So I will not go into the detail, but I want to emphasize that when we say fuzzy sets, we do not mean one particular type of fuzzy set, but there's also a number of classes, number of types. And each of these classes has its own kind of calculus, its own rules, of operation and so forth. So there's a multitude of these. And then on the basis of fuzzy sets and the fuzzy set theory with all the operations involved is utilized for developing fuzzy logic by which we can facilitate reasoning in natural language, in some sense, and that is by using the various types of fuzzy sets for defining predicates. Predicates now are represented by fuzzy sets. The qualifiers, truth qualifiers, probability qualifiers, and so forth. Quantifiers, fuzzy quantifiers, and so forth. So the elements of the fuzzy set theory are kind of components, fuzzy set theory and fuzzy relations and all of that, are components by which we then build, the calculus or whatever you would call it for fuzzy reasoning. for fuzzy reasoning, and that is a very good way of representing natural language and reasoning in natural language, and that in turn can facilitate reasoning with perceptions in some sense. This is currently, there's a lot of research going into that. The perceptions is still not fully developed, but the utility of the fuzzy set theory and the fuzzy logic based on that, via representing natural language and natural language representing perception, that's the way, except that it is not fully developed yet. And then I added here in the formalized languages also rough sets. Now, a rough set is something very different from fuzzy sets. In rough sets, we have a kind of, we define an equivalence relation on the universal set with which we work, and represent an arbitrary set, of subset of that universal set in terms of the equivalence classes based on that equivalence relation. And we do that approximately, roughly, therefore it is called a rough set. We do that roughly by lower approximation and upper approximation. The lower approximation contains all the equivalence classes which are included in that set which we want to represent, and the upper approximation contains all the equivalence classes which overlap with that set we want to represent. And in between the set which we represent is somewhere in between the lower and upper approximation. But we represent the set strictly within a limited resolution based on the equivalence classes, okay? So that's a different way. But the point is that we can combine these two, and if you combine them, you have two possible combinations. And by combining, we are gaining. We are getting much greater expressive power again. One is when we use fuzzy rough set. Fuzzy rough set would be basically a rough set, but now the equivalence relation is not a classical crisp equivalence relation, it's a fuzzy equivalence relation. And a fuzzy equivalence relation would be a relation which at every, what we call the level set, is a classical equivalence relation, but it's a multitude of equivalence relations, potentially infinite set, which are nicely organized from less refined to more refined. So that is one. The other combination of rough fuzzy sets is basically a fuzzy set which is approximated roughly by a rough set. And in this case, it's a fuzzy set, but its level cut are approximated by a rough set via some underlying classical crisp equivalence relation. So there are two different combinations, and you can see recently there's a lot of applications of these combinations. There are several books came out of that in all kinds of areas. And I should also mention one interesting thing about fuzzy sets here. When we develop fuzzy logic and when we use reasoning using fuzzy propositions of all kinds, quantified, qualified, whatever, then it is established mathematically that when we use the reasoning using fuzzy logic, and at the end of the reasoning we use so-called defuzzification. We defuzzify, so that we, after the reasoning, we obtain a fuzzy set as a result. But we defuzzify. Defuzzification means that we represent the resulting fuzzy set result of the reasoning. We represent it by one real number, which in some sense best represents the fuzzy set. Okay. Now, if we do the defuzzification, at the end it is established mathematically that a fuzzy system, a system of if-then rules, inference rules, fuzzy inference rules with a defuzzification, is a universal approximator. So every arbitrary function, linear, non-linear, whatever you have, any arbitrary function can be, with desired precision, be approximated by the system. Okay, so you can, whatever you can do, let's say with nonlinear differential equations and so on, you can do in this way also. So I view it as a very alternative new way of doing science, rigorous science, because we can, whatever you can do that in the classical way, by classical mathematical analysis, you can achieve in this way. Now the advantage is that this approach is very much keeping in touch with the intuition, with the common sense, because it is based, again, on the natural reasoning in natural language. But eventually you can make it as precise as you want. And this is what I recently experienced in one particular application area, and that is geology. I recently started to work with a colleague in geology, and using this kind of approximator, using the reasoning in fuzzy logic for geological problems, namely problems of forming sediments, sedimentation, we can not only reproduce exactly what has been done by very complex sets of partial differential equations and so forth, but we can do better. We can do better, and we can do that in an intuitively meaningful way. In other words, my colleague in geology tells me that in geology the true knowledge is expressed in natural language. And then later they wanted to make geology respectable, so they started to use differential equations and so forth and so on. It's a little bit too precise for that problem. Geology, all this wind and size of the particles and so forth, this is not, there's no clear cut. So he says, the true knowledge in the old books was always in natural language. The more modern, they started to use, partial differential equation. But he said, now we have a new tool, and we can go to the original knowledge and actually represent it in a different way, in a much more natural way. So this is really, I see this as a very significant, because it sort of develops a totally new way of doing science. And I think we are at the very beginning of that, but we already see some kind of very, very good results. So that is about these new extensions in the formalized languages. But now, if we want to deal with uncertainty, actually see what kind of types of uncertainty we have and how far we can develop it, then we need also the second dimension, and the dimension is that we have to somehow represent the knowledge, the evidence. Okay? Logic is not dealing with the truth. It deals only with the combination, and so forth. But the actual epistemology comes from outside. We have to represent it in some way. So like what we do in classical numerical probability theory, we use classical set theory or classical propositional calculus, and then we introduce a measure on that by which we express our evidence, our evidential claims, right, about the events we are interested in. Now this would be the classical probability theory, would be this box here. We combine classical set theory with the classical additive measure, and that would be the probability theory here. Now, the additivity of classical probability theory, additivity means that if I measure something for one set and another set, these two sets are disjoint, then the measure for the union of these two sets is a sum of the measure for the set. But this is very restrictive. This is very restrictive. This kind of implies that we assume that these two sets, whatever we measure in these two sets, are entities which are non-interactive, totally no interaction. So it is very restrictive. So recently, there is another new dimension, new development, which is dealing with measures which are not additive. Non-additive measures, or sometimes we call them monotone, sometimes we call them fuzzy, the fuzzy is not correct here because really no fuzziness is involved, it's just a historical term. But we have these non-additive measures where the additivity is not anymore required, but we only require monotonicity. And that opens a totally new dimensions. For example, you can deal with imprecise probabilities, you can deal with possibilities, and so forth. So there is a lot of new theories which developed along this line, because now you have this framework of monotonic measures, which are monotonic with respect to substitute relationship, but they are not additive. So they are much broader. The additive measures are just small part of it. And so now if you add some additional requirements, this or that, you get number of different special subtheories. So there is a new extension here. Now, so you have one extension here, you have one extension here, and of course, you can see, how much work we have to develop all that area here. Some of that has been developed, but we still have a lot of other things to do. So, for example, most of these areas still based on classical set theory, but non-additive measures like many types of imprecise probabilities and so forth. This has been pretty well developed. Also, the possibility and necessity measures for fuzzy sets, this area has been pretty well developed. But there is still a very large area which is sort of underdeveloped. And for each of these boxes which you see here, we really need to develop the representation of uncertainty at that level. We have to develop the calculus to manipulate that uncertainty at that level. We have to develop a measure, like in probability theory, the Shannon entropy. We need to develop the measure of the uncertainty, and then the principles based on that, and the methodology, and so forth. So there's a lot of work. So I see it as a huge program, and this is what I have been interested in. Now, I think the time is running very short, so I cannot properly answer everything, but I even didn't touch the soft computing. The soft computing really is an important part of intelligent systems, and by soft computing, what we mean is a kind of partnership of several different areas. This is fuzzy logic and the reasoning based on fuzzy logic. It is the neural network area, which we use actually for tuning the membership functions and the operations, right? So as I mentioned, if you learn certain tasks like parking the car, first instructions come in natural language. You are taught what to do and how to do that. So you have natural language, but then you have to practice and actually learn the skills. So here neural networks actually represent that part. They can be combined with fuzzy logic and fuzzy systems, and they represent the learning aspect of that, the tuning of the membership functions and so forth and so on. And then we have evolutionary programming, evolutionary, genetic algorithms and that area. And probabilistic reasoning, which is based not necessarily on classical, but imprecise probabilities also, and various kinds, and rough sets and so forth. All of that partnership, all of these tools together is usually referred to as soft computing. And the soft computing is what I mean is this new area, the alternative kind of direction in science, using soft computing rather than hard computing. And if we want to kind of take the human mind as a model in designing intelligent systems, then the soft computing is crucial here, because as I mentioned, we perform these tasks based on perceptions and processing with perceptions. So we need some tools to deal with perceptions, and the hard computing would not do that. So what we need is to use the soft computing. Of course, these are all very, very complicated, topics and so forth. So in this very short presentation, and I understand I have to stop right now, I could have only answered them very, very briefly. So thank you very much for your attention.